Welcome to RITMO Largo. It's so wonderful to see people in this room after 2 years with hybrid and online format. We're still hybrid, but there are more people here now than we have had here for actually for a couple of years. So that's wonderful. We have an exciting program. We start with our presentation by myself and Alexander. Then we have a RITMO seminar series with Nicola Dibben, and then the thematic panels in the afternoon. And we round off the whole thing with a reception in the RITMO kitchen. And we also have an installation and fika and lunch. Yeah. So enjoy the day. But first, a music performance. Alexander.
This is just to show you the different parts of the day. And we'll start with the performance. And one of the important things at RITMO is to do research. Another important thing is that we do research education, and we do research-led education, research-based education. And an important element here is that the PhD fellows and postdocs at RITMO teach in various ways. And now we'll see the result of two of RITMO's PhD candidates, I could say now, because both of them are going to defend their thesis later this year. Çağrı Erdem sitting here, and Çiçao Lan is sitting out there in the world. He got corona, unfortunately. But they finished their PhDs before Christmas, or their dissertations, and now this year they are doing a completion grant, which means that they have a year to do teaching and supervision and also research. And they are leading a small ensemble of students from the Department of Musicology in a course called Interactive Music. And we thought that they should start off this event by playing a little for us. So please welcome I'm not sure if you actually have a name, the students from the Department of Musicology under the leadership of Çağrı Erdem and Çiçao Lan.
Ist ein Herr von Land zu Land. In meinen Haaren spielt der Wind mit seiner schlanken, braunen Hand. Ich bin allein, nur hier und da spiele ich mit einem kranken Ring. Ich halte Schnüre in der Hand und es sind auf ihnen aufgereiht all die Tränen, welche je ein blasser Mädchenmut geweint. Sie alle habe ich geraubt, bei schranken Mädchen spät bei Nacht. Denn mit der Sehnsucht Hand in Hand, sie bang auf langen Weg gewacht. Ich bin der Regen und ich bin barfuß einher von Land zu Land. seiner schlanken, grauen Hand.
Thanks to the students and to Tare and to Chao as well. Then we'll move on in the program.
Yes. Now to RITMO. Thanks to the performers, thanks to the students, to Chara and to Joe. We presented the program. Let me see. Yeah.
We will start with talking a little bit about RITMO and where we're coming from and where we are at the moment. And we started 5 years ago with this group of people coming from 3 different departments: musicology, psychology, and informatics. And together then we have, over these years, we have been able to establish RITMO as it is today. And it's RITMO's phase 1 that we're mainly going to talk about today. But one of the things that, and one of the reasons we wanted to do it like this is also because right now we are thinking a lot about RITMO's phase 2, which is coming up very soon. So obviously this is a good time to kind of put a foot in the ground and think about what we have done so far, and not least where we are going. So that's kind of the agenda of today, really, is to try to talk about this story. And of course, we're also very interested in trying to figure out what's going to happen after RITMO. And this is a bit strange, leading a research center that's lasting for 10 years. 10 years feels like a very long time when you start out. But then when you're in the middle of it, time really flies, I think.
Yes.
So we have already now started thinking about this question mark at the end. And that is also going to be the topic of the Scientific Advisory Board meeting we're going to have tomorrow. But that's only for some of you. But today, the main focus is on phase 1.
Yes, as you know, the core of RITMO is rhythm. And we are both interested in the basic structures and features of rhythmic phenomena. We are interested in the mechanisms underlying human perception and cognition of rhythm. And last but not least, are we interested in the link between those 2 things. We have a very large and impressive infrastructure. Alexander, you want to present some of that? Yeah?
Yes, that's one of the interesting things about RITMO, is that we have very theoretical differences where we're coming from starting points, but also the methodological differences. And we are covering everything from what we call the soft to the hard. And you can say that on the soft side, if you call it, we read books, we even write books. Also coming more from the music side, we are eager also to analyze music in form of scores, but also in terms of sound. We do different types of interviews individually and with groups. We do questionnaires and surveys. We do motion capture, looking at how the body moves in different ways. We also do eye tracking and pupillometry. We do studies of the brain, such as EEG, but also fMRI. And we do machine learning of different kinds, artificial intelligence, and also robotics. So as you see, we're covering fairly broadly from really then the soft to the hard, if you like, but not least also looking at how it's possible to combine these different methods. That's something we are increasingly trying to explore. Then when it comes to RITMO and our organization, it has already changed within these first 5 years. Right now, this is the current organization of RITMO into 4 research clusters. And this will also kind of form the way we will present this to you today. As I said, we already changed this once, and we might change this again as well, because this really depends on the people involved. And talking about people, what we also are working on now is trying to figure out how, one thing is the faculty members and how the way we are working together inside of RITMO in different ways, and we see new interesting constellations there. But of course, also the fantastic people that we have with us, which is really a growing number of people. And when we asked about how many people work at RITMO, we always it's always a bit difficult to say, because there is so many people coming and going, and also at any point in time we have so many visitors and guests. But we are 50 plus full-time people working at RITMO now. So we are kind of grown to become a sizable center, I think.
Absolutely.
I think that's it for me now, and I guess you will start with the cluster presentations.
Absolutely. I just wonder if there's. Whoops! Wait. Yeah, a little bit of.
We can take it down.
It's yeah. Okay. We need a little wake-up call there. Okay, I'll start with the structure and cognition cluster. The aim of the research in this cluster is to reveal the effects of rhythmic and temporal features on cognition and the neural mechanisms involved. And in this cluster, we use a variety of methods. We use pupillometry, functional magnetic resonance imaging, or so-called fMRI. We use also scalp and intracranial EEG. And we recruit both healthy participants and special populations, such as musicians, for example, synesthetes, and also neurological patients with focal brain damage or epilepsy. I will focus now on 2 articles that have come out of this of the research in this cluster, and the first is authored by Maja Foldal.
The world around us, our surroundings, they are full of regularities in shifting traffic lights, when we speak to each other, or when we listen to music. We use these regularities to anticipate or predict when things around us is going to happen. What I find almost magical and incredible about this is the fact that the brain seems to be tracking what's happening in the background, these regularities, even when we are focusing on a very specific task, and I really want to figure out more about this. I am Maja Foldal, and I'm a PhD candidate at RITMO.
Great. Maja is now a postdoc in RITMO, and but in this article, she and her colleagues report on findings from scalp EEG recordings in healthy adult participants who listen to rhythmic sound stimuli. And they used a so-called dichotic listening task, and the participants, that means that 2 streams of sounds were presented, to one to the left ear and one to the right ear, and the participants were instructed to pay attention to either the left or the right ear and ignore the sounds in the other ear. And then they compared the high predictability blocks with low predictability blocks, and you see here that in the high predictability blocks there were less irregular events than in the low predictability block. And interestingly, there was no interaction effect between attention and predictability, which means that the effect of rhythm predictability was present for attended as well as unattended tones. And you can see that the early perceptual response, which is the so-called N1 in the illustrations to the right, it was reduced in the high predictability condition for both attended and unattended streams. Here we depict the results of 2 frontal electrodes. And this is actually the first study to show that the brain predicts the timing of sounds even when they occur in the background and attention is directed elsewhere. The next article that I will talk a little bit about is first authored by Alejandro Benkman.
So the reality as we perceive it is not only representative of the world we live in. For example, when seeing a ventriloquist show, we see the voice coming from the puppet's mouth and not from the ventriloquist. So how is that possible? So to put it simple, the reality is built from the interaction of predictions coming from inside our brain and inputs from the outside world. Understanding how these predictions are computed inside the brain is fundamental to understand how the brain works in normal but also in pathological conditions. I think that it's just curiosity. How is that this group of neurons, cells in the brain are doing all this magic, right? Because we perceive the reality as something that is continuously flowing. We don't realize that actually what is getting into our brain is just electrical noises, very noisy signals. And we don't perceive anything of that, right? My name is Alejandro Bleckman, and I work as a researcher at RITMO.
Yeah, the insula, which is the kind of area of the brain in focus in this research, is one of the least understood brain areas. And in this paper, Alejandro and his colleagues in the Front Neuro Lab and also at Berkeley and several places in the world, actually, this is a kind of a network of researchers. They reported on invasive EEG recordings. Invasive means that it's actually recording signals from inside the scalp. And the recordings were done on epilepsy patients that were waiting for surgery. They listened to sequences of expected, standard, and occasional unexpected deviant sounds, differing in 4 physical dimensions: intensity, frequency, location, or time. And the figure to the left is an illustrative map of the subdivisions in the insula, this brain region, with recorded channels from all the subjects that were part of the study. And the figure to the right shows the average high frequency, that is the gamma response to standard and deviant tones from all so-called condition-specific channels in a sub-region of the insula. And this region is entitled inferior circular sulcus, for those interested. Oh, yes. This area had increased and later responses to unexpected compared to expected sounds. Shown, and this response is shown in red.
11 or 11:30, 11:45.
Yeah, we have an intruder, and it sounds like Mike.
Yeah.
Perhaps someone could just. It's actually kind of a warning of the installation that's coming up after this presentation. So, yeah, very effective way of drawing attention to the next thing in the program. So that's good. Well, okay, this area, this inferior circular sulcus, had increased and later responses to unexpected compared to expected sounds. And this response is shown in red across the types of deviance studied. And this is the first direct neural evidence that the subregion of the insula is engaged during automatic auditory deviance detection. A few words also about plans for phase 2. We want to do more studies of cross-modal integration. We have already investigated whether sight can change what we hear, and the answer is, in short, yes, and came out of a study where Bruno Laing and colleagues investigated whether such kind of cross-modal integration of sight and sound, the so-called McGurk effect, generalizes to vocal articulation by singers. It has previously been kind of associated with speech primarily. And we will continue our research on cross-modal integration in phase 2. I also want to mention a project that we have just started with. Its focus is on rhythm as an individual ability. And here we ask how and why do rhythmic abilities vary between individuals? We are interested in the factors that shape the human sense of rhythm. And as part of this, we are developing a test battery that covers everything from microrhythm to hypermeter. And the aim is to complement existing tests and better understand the relationships between different temporal levels of rhythm perception and production, and how these different abilities are organized in humans. And we also look into relationships between these rhythm abilities and cognitive abilities, like more general time cognition, cognitive control, attention, working memory. And last but not least, we were involved in a twin study where Heidi over there is the kind of the principal investigator from the RITMO side, where we investigate the heritability of these rhythmic abilities. So I guess that's the report from the structure and cognition cluster. I'll move then to the structure and time cluster, which I have been leading in this first phase. And here the core questions are, what part of a musical beat's sound constitutes its temporal position? When does a beat happen in time? Might seem like an odd question, but it's actually quite interesting. And how do sonic and temporal features interact at the micro level of rhythm? And how does our experience of musical rhythm vary with our experience, and also perception of rhythm vary with people's music cultural background? We have, in the so-called time project, which has been focused on interactions between temporal and sonic features at the micro level of musical rhythm, we have done both qualitative and quantitative research into these kinds of interactions. And in the so-called quant part, as we call it, we have conducted a series of perception experiments where people were asked to align either a click or tap to different target sounds. And then we systematically varied acoustic factors such as attack, duration, and frequency. And the results show that the attack shape and duration impact both when we perceive a sound event to happen and also the precision with which we do this. And in a second experiment, we investigated how expertise in a specific musical genre affects such low-level perceptions of sound. And we recruited then 3 groups of expert performers, jazz musicians, Scandinavian folk fiddlers. It's a very kind of particular Scandinavian fiddling tradition, this one, and also a group of hip hop and EDM producers. And they were presented with both familiar sounds from their own genre, from the other genres, and also some neutral sounds, just noise sounds. And we found some very interesting group differences, especially the fiddlers hear the timing and synchronize to sounds from their own genre differently from the other groups. And what was interesting with this particular group, which has a very, very flexible timing tradition, is that we expected them to be more precise with their own sounds, but they were actually more flexible with their own sounds probably because the tradition kind of demands this flexibility. And we think that this sheds light on the role of active long-term musical enculturation in the development of our perceptual system. So this is also something that we want to pursue in phase 2. We also looked into how timing and sound features interact from the perspective of performed microrhythm.
What is groove and how do musicians create it? To that question, world-class musicians such as the Red Hot Chili Peppers might answer, if you have to ask, you'll never know. Though they would also add that funky motherfuckers will not be told to go. However, here at RITMO, we attempt to grasp the seemingly ungraspable, striving to quantify and qualify what it is that makes groove-based music so unique and ubiquitous in the world today. In my PhD research, I investigated how temporal and sound-related properties contribute to the production and perception of rhythm in groove-based music. While precise timing and performance is considered a hallmark of groove playing, when used in a controlled, flexible fashion, performers can convey a multitude of aesthetic, qualitative effects by playing either straight on, slightly behind, or ahead of the beat. Through a series of performance experiments with guitarists, bassists, and drummers, I looked at how musicians manipulate a wide range of acoustic features to create different so-called microrhythmic feels in groove. By analyzing audio and motion capture data from hundreds of performances, I found that while timing is indeed important, it is but one of many features involved in the production of groove. In addition, a range of tacit sound features, such as duration, intensity, and brightness, can also play a key role in communicating different groove feels across various genres. My name is Dr. Guilherme Câmara, and I'm a postdoctoral researcher at RITMO.
Yeah, so Guy Camara did performance experiments with guitarists, bassists, and drummers, and here are the results from the guitarists and the bassists. Regarding timing features, we found that on average, participants place their strokes around 40 milliseconds earlier and later in time in the pushed and laid back conditions, respectively, compared to the on-beat condition. And this demonstrates the high degree of deliberate timing control that expert musicians can have. Not very surprising, perhaps, but it has not yet been experimentally demonstrated for guitarists and bassists. But we were most interested actually in the sonic features, and we found that the musicians also used changes in sound features to distinguish between the timing fields. And interestingly, they used them in accordance with the results from our perception experiments. So it seems that they use these sonic features to emphasize the perceived earliness or lateness of the strokes. And overall, the findings of these studies show that that relative lateness and or earliness of sounds may be enhanced or attenuated by way of so-called strategic timing sound combinations. For these experiments, which kind of comprise a huge amount of data points, Olivier Lartilot and the Mirage project developed a new tool that made it possible to automatically localize the attack regions of the performed sounds with extreme precision. And this was needed because previous methods were actually too imprecise, because here we work at the millisecond level and previous methods couldn't capture that. And that was published in JASA. Okay, in the qualitative part of the project, of the TIME project, we have interviewed musicians and producers in 5 musical genres: jazz, samba, hip hop, EDM, and Scandinavian fiddle music. And they were asked about whether they explored so-called these timing sound interactions in their work with grooves. Of course, we asked more openly. We didn't kind of force this concept upon them, but it turned out that they actually were very aware of such interactions. And here is an illustration from an article in Music Theory Spectrum, where we report from the interviews with the EDM producers and also analyzed the multitracks of their music, because they provided us with multitrack projects, which was really interesting, because then we could actually compare, we could take out some of the effects that they had used and compare with kind of neutral versions of the same things. So, and it shows that this EDM producer, which has a clear preference for a kind of a grid-based micro-timing aesthetic, they are still very sensitive to and adept at manipulating timing for expressive effect. And this particular example shows the use of swing quantization in Sieb's remix of Mark Posner's I Took a Pill in Ibiza. I think it's still on the Spotify top 100 or top 300 list, so it's really an international hit. We also investigated sound motion relationships, for example, music and dance.
When we experience music, we don't only do that through our ears. We use multiple senses, so the music is multimodal. And I'm particularly interested in the music and motion correspondence. I use a motion capture technology where I place reflective markers on the bodies of my participants. And based on this sound and motion recordings, I can do analysis where I look at both the sound and the motion together to get a better understanding of the rhythm structures in these music styles. I'm Mari Romarheim Haugen, and I'm a postdoc at the RITMO Center at University of Oslo.
Well, unfortunately, Marty is not a postdoc at RITMO anymore. This is a video from a couple of years ago. But Journal of Music Theory recently released a special issue on music and dance. And in the opening article of this issue, Mari develops her ideas regarding how to study rhythmic structure as an interaction of motion and sound. And in the illustration shown here, she extracts the beat structure of the fiddling by analyzing the motions of the dancers. And she argues that dance and other genre typical movements are integral to understanding musical rhythm. The study of rhythmic structure as music dance relationships will continue in phase 2 in the project Djembedans, which will focus on polyrhythm in music and dance from Mali with Rainer Pollak as the PI. And another phase 2 theme grows out of Ragnhild Breivik Hansen's work in the MESH project, where it's a monograph entitled Parody in the Age of Remix, based on her work in this project, is forthcoming on MIT Press in 2023. And here she approaches mashups and remix music as something at once familiar and new, expected and unexpected. And similar to polyrhythm, such phenomena take place at 2 levels simultaneously. And we want to take a closer look at the aesthetic and cognitive aspects of such what we call dual plane temporal experiences in phase 2. Yeah, I guess that was it from the structure and time cluster. I think now Alexander will lead us into a physical exercise. We need some
We will
motion.
have a little intermission, and instead of coffee and croissants that you can have more later, we thought we should do a little bit of music and movement. So if you could all rise, please. And then we're going to teach you, for those of you that don't know it from before, we'll teach you a little bit of Norwegian. So if you can just click on this. This is hode, that's the head. The next one is skulder. And then on the kne. Kne og tå. That's down there. Okay. And then we can go even a bit more. If you want to look at the anatomy of the head, we can do what we have here, Anne. We have the øyne, middle, yeah, ører, and kinn og klappe på. Okay. So are you ready for this? And then of course we start slowly, and then we'll see how it goes.
Hodet skulle kle og tå, øyne, ører, tå. Hodet skulle kle og tå.
And then it's a bit faster.
Hodet skulle kle og tå. Hodet skulle kle og tå. Oops.
We can try more after if you like. So this leads nicely into our next topic, which is interaction and pleasure. That's also something we explore at RITMO. And here we are particularly interested in the processes and phenomena underlying rhythmic interaction and action, and also the effective outcomes of these processes. So we try to look at different things. And one thing is to understand why rhythms make us move in the first place, like you just experienced, and also increasing rhythm make you move differently. how written facilitates entrainment and interaction. Again, what we experience now was some kind of entrainment also going on, quite complex, I would say, in this group of people. That could be an interesting research topic on its own, I guess. And then also explore the effective and social outcomes of such processes. Again, as we just experienced, music is also very much kind of a social activity. So this we try to study. And in this cluster, which I guess is the biggest one at RITMO right now, we have it's a lot of people working on topics related to this. It's a highly multidisciplinary group of people as well, covering everything from philosophy, various branches of musicology, psychology, and also informatics. And we'll look at just a few examples of this. Again, what Anne and I are presenting here today is just kind of a few glimpses into everything we're doing. There are so many other things too, but we have to select something, I guess, for you so that this doesn't run the whole day. So let's start by looking at a video.
From previous research, we know that music has fantastic effects on people's moods and on their well-being in general. And I particularly focus on the kinds of experiences that playing music generates in the people who play it. I do that because those experiences are very intense. They're like the crystallization of what it means to be exposed to music and to art. And I'm interested in finding the core of this phenomenon, because if we can find that, I can perhaps say something about the general structures of it and how to bring it about in more instances. I'm Simon Hofting. I'm a postdoc here at the RITMO.
So Simon has moved on now. He's not any longer a postdoc here, but an associate professor in Denmark. He contributed, among many other things, with a book on the phenomenology of musical absorption. And this idea of absorption is something that has been carried on at RITMO, and also together with Simon in his new position. We have recently organized the Music Lab Copenhagen that I guess many of you participated in either in person or virtually, where we were able to collaborate with the Danish String Quartet, a world-leading string quartet, and basically overtake a full concert that they were doing in Copenhagen with 150 physical audience members, but also several hundred virtual participants in this performance. And not only did they kind of allow us to take over their concert and do research on it, but they were also sport enough to actually dress up in motion capture suits and with physiological measurements and eye tracking, etc., during the actual concert. They also allowed us to do experiments with them before and after the concert as well. So this is a fantastic kind of data set that we are working on right now. The concert was actually 2 years delayed because of Corona. So meanwhile, we had the opportunity also to develop various things. I should mention that we're also working on a special issue in Music and Science that will come out with a lot of material from this concert. But before we came there, we had also a concert here at RITMO with a student string quartet from the Norwegian Music Academy. And they allowed us to study their exam concert here in the lab with a similar type of setup so that we can use this as a practice session for the other session. We also did a music test lab over at the university library because, again, with Corona, we weren't allowed to travel and only meet with few people. But then we did this, what you could call slow TV, which is a Norwegian tradition, for kind of exploring something that takes a little bit of time. So we had a full day of research slow TV where we streamed live the RITMO researchers setting up the whole thing, running a concert and then taking everything down again. And it's online if you want to watch 8 hours of researchers moving equipment and talking. That's available for free for everyone. Talking about the Music Lab Copenhagen concert, which then finally happened in October last year, we were also very fortunate that we received the Danish radio's P2 prize for the event of the year for this show, which kind of is also a testament for that this type of research can both be entertaining but also actually have a value beyond the kind of the entertainment part of it. So that was a great recognition of our work. Now, I guess the main point here of what Anna and I are presenting today is more the results. And of course, we don't have much results from the Music Lab Copenhagen yet, because we are still very much into just kind of organizing all the data and analyzing, etc. So more things will come out in music and science. But I could mention a few things that we think will come out. And this is based on some published articles by Laura Bishop and others here at RITMO. And with data from then this student concert that we did down in the motion capture lab a couple of years ago. And one thing that that we found out there was looking at also the different kind of relationships between what's going on in the bodies of people and in the eyes of the musicians and the results. And it's I cannot go into details, but it's kind of a complex relationship between different types of performance kind of measurements, and also both in the kind of experience of this and also the output of this, related to both bodily effort, the musical complexity, and also the expressive difficulty, if you like, of the music in play. Another interesting thing that happened there, and this is just also something to say about, sometimes we're just lucky, you could say, in a research context. And in this particular concert, then in one of the pieces, the first violin happened to try to turn the page of the score and failed. And obviously, that is kind of a stressful situation when you are doing your exam concert with an audience. And we managed to capture this with eye tracking, etc., which is then super interesting to look at, because we can then really look at stress levels, and you can also kind of see the really spikes of the red, the first violin, the red thing up there, when you see kind of the line of where this kind of page turning failed. So that's again, sometimes you are just lucky as a researcher to capture these type of things along the way. There are so many other interesting things to talk about, and one of the things that we also have explored now with the Danish String Quartet is to run an experiment with them before the concert, and this was similar to what we did with the student concert, and that Laura and others have already published on, where we asked the musicians to play the same piece in many different situations. One thing was sitting blind. The first one there, they're sitting with kind of their backs to each other, so they couldn't watch each other. Then focusing only on the score, then a normal condition, then isolating the violin from the other, so that the first violin wouldn't see, they couldn't see each other. And then different, one kind of replication of the rehearsal, and then kind of a concert setting. And again, there are very many interesting things to look at here. For the student group, we found different levels of quantity of motion for the different pieces. So that's kind of something we're digging into more now, and trying to see, is this the same for a kind of world-class string quartet that it is for a student quartet? And also, there are interesting things happening also when it comes to the gaze and the direction of where you look. And we do see that many of the other musicians look more at the first violinist, as kind of many people would expect. But there are some interesting patterns, because we can, since we can tracking all of these separately, we can also look more systematically at how they look at each other over time. So again, lots of more interesting things to come here with when we manage to get all the data from the Music Lab Copenhagen analyzed. Okay, let's move on.
When people listen to music, they often spontaneously start moving to it. It just feels natural to nod your head or tap your fingers to the beat. So natural that it kind of seems to be happening without your control, maybe automatically. But is it indeed automatic? Can we decide to move or not to move to music? In other words, do we move to music, or does music move us? My research suggests that it can be very difficult to not move to music, even when you really try to stand still, which we showed in several motion capture experiments. I want to understand how and when music moves us, and why it can be so irresistible. My name is Agata Żelechowska, and I am a researcher at RITMO.
So Agatha worked in the micro project that I was leading, and it completed last year. And it was also Victor Evarista Gonzalez Sanchez was also a postdoc in this project. And the core kind of research paradigm that we worked with was that of standing still, taking people in either individually, as in this experiment by Agatha, but also we have been running the Norwegian Championship of Standstill for several years to kind of have larger groups of people coming in. And by the way, there will be a European Championship of Standstill this year in Oslo, 4th to 6th of May. So if you're interested in participating, then it will be down at in the center of Oslo to come and compete there. And the idea here is to look at how music makes us move, even if we try to resist moving and standing still. So we play music to people, and we have silence, and we do this in the controlled conditions, and try to then measure what's going on. And then what Agatha did in one of her articles was to look at also the difference between headphones and speakers, and are there differences between headphones and speakers when you do this task. And we did find that if you're standing with headphones, you move a little bit more to music than if you only have listen with your ears to speakers. And that may not be entirely intuitive, and we discussed that a lot in this paper if you're interested in reading more about that. Another paper, we also looked at the individual differences when it comes to moving. Are some people more kind of prone to moving than others? And yes, we did find that empathic concern is one element that predicts more movement to music than others. Then a lot of this data also from these studies is now also available from the Oslo Standstill database. So that's another thing we have been working on at RITMO, is trying to figure out how we can work on open data perspective. So if you're interested in that, there are 600 recordings of people standing still there, and also various toolboxes developed for this, packaged up in the musical gestures toolbox. Now, Agatha's experiments here with the empathic concern and individual traits is also linking up very nicely to kind of a series of experiments and results from Jona Woskoski working here at RITMO, looking at, again, this feeling moved by music. And in this particular paper, she was looking at this from different ratings of, and trying to kind of combine and looking at different relationships between acoustic correlates to the continuous ratings of these different types of music. And this is kind of something also that we're going to explore more in phase 2, kind of coming out of this cluster. We see that this kind of social bonding, if you can call it, is something that several people are working on right now, where we have a lot of the results of Jona Woskoski and also Nanette Nielsen here working on these things. We have done a series of cool studies of Corona concerts by Dana Swarbrick, a PhD fellow here now, and of course also all the material from Music Lab Copenhagen. So that will certainly be something that we're working on as we're moving on. Another kind of line of research that we have been working on is kind of also developing from both my own work on kind of the micro and into the kind of the ambient project, but also the work of, for example, Bruno Lang, Nanette Nielsen, and also Ragnhild Brøvig Hansen being very interested in audiovisual experiences, not only looking at auditory aspects, but also the combinations of auditory and visual experiences in different ways, and also cross-modality, if you like. So that kind of summarizes a lot of what we've been working on in the interaction and pleasure cluster, but we also have an interaction and robotics cluster. And here, this is more kind of on the technology side, you could say. And the aim here is to look at how we can think about rhythm and motion when we work with interactive systems and robotic systems. So here, there's a lot of kind of exploration of making interactive music systems, also that you got an experience of earlier with the students playing, but also then working with robotic systems, both kind of systems that we build ourselves, but also pre-existing robotic systems that we work with.
Can we teach an artificial intelligence to dance? And why on earth should we? When we see a dancer's movement, we often make assumptions about what music might be playing. If you look at these two people, I think most of you will get an idea about what music was playing while these dancers were recorded. My work is focused on trying to see if these sound motion mappings is something that can be learned by an AI. I've collected a data set of motion capture recordings of dancers improvising to different music. And I use this data to train a deep learning algorithm to see if it can learn to dance. The AI consists of an artificial neural network that has recurrent connections. And this allows it to hold a sort of short-term memory and remember the things that it has seen. Sometimes it does strange things, and sometimes beautiful things. Teaching AI to do creative tasks like dancing could teach us about our own artistic processes and augment our creative practice. My name is Benedicta Wallace, and I'm a PhD candidate at RITMO.
So Benedicta has been working on this kind of looking at motion capture and how we can not only analyze motion capture, but also create motion capture in different ways, or motion animations. And this kind of, now my slides are a bit strange here. This ties also into some of the work that has been done by Çağrı and others here as well, looking at how we can kind of use artificial intelligence and machine learning of different kinds to kind of explore creative practices. And one example here is also how they worked with looking at guitarists and doing motion capture and also muscle sensing of these guitarists, and then analyzing this material of different types of kind of, you can call it action sound couplings here, where you have kind of looking at the energy profiles of the EMG, but also the sound and also the motion, and trying to see, can we train a system to learn these kind of relationships? And then one thing is can you train it to learn that? You can also use that in creative practice, as we did in a music lab as well, where this new kind of, as Çağrı calls it, AI toddler, because it hasn't really gotten much further in its development, how a human performer can perform together with this this machine intelligence and have a meaningful musical conversation.
I study human-machine interaction in creative contexts. How humans and machines can collaborate together on creative activities. I'm interested in building robots that can listen to rhythm in the environment, such as a person might be playing, and then can analyze that rhythm and respond appropriately by improvising its own rhythms. So what really inspires me about the work that I'm doing at RITMO is that it really occupies very firmly that middle ground between art and music on one side and computer science and engineering on the other side. And RITMO has been a really good environment that nurtures that in-between space. My name is Michael Krzyzaniak, and I'm a researcher at RITMO. Yeah, so this is Dr. Squiggles. Everybody I show this to just wants to know whether or not I knit this, and I did. Nobody's impressed by the fact that I made a robot. They're only impressed by the fact that I knit this.
And in not many minutes, you will be able to interact with Dr. Squiggles, both with the knitted hats and not. So we will walk down to the lab in not too long and hear Mike talk about this down there. But in terms of the research, it was very cool to see Mike's robots featured in the Make magazine with kind of really detailed descriptions of how you can make these robots yourself. Including the knitting part, how you can make these things work. But then, of course, this is also part of also basic research into kind of how we can look at human-robot interaction. So in this particular article here, Mike has also published on the model behind this and how how the thinking about also the kind of the rhythmic generation and the interaction between the kind of the machine rhythms and the human rhythms work, and kind of also laid out this kind of and analyzed the different patterns that you may experience with this. And one of the ideas also here is to try to see not only if a robot can interact rhythmically with you, because it surely can, but then it's also a question about whether it's interesting or not, and what does interesting mean in this context. That's something that Mike is concerned about. Another part of kind of our robotics work is this very interesting creature here called Dyre, which was built by Tønnes Nygaard and also others, and it's a quite fascinating quadruped robot with a lot of technology and sensors built in. And the interesting aspect of this robot is that it can also self-adapt, so that it can, for example, walk on different materials, so that it will sense what type of material it's walking on, and then it will adjust its legs to the right length, so that it can kind of optimize its walking speed for the different conditions. And this led to a very interesting kind of piece of work that's also featured in Nature Machine Intelligence. Now, this kind of human-machine entrainment, if you like, is something that we are going to continue exploring in phase 2 of RITMO, because we see that there is so much potential here. One thing is the robot-robot and human-human, but also then this human-machine and human-robot type of interactions. And there we kind of particularly see that this entrainment aspect, how we can rhythmically can interact, and how the kind of the different rhythms of the systems can interact. That's something that we want to explore further. And we also have an interesting other line kind of robotic activities now with a new project called PIRK, led by Jim Tørresen, where we're looking at the predictive and intuitive robot companions, and kind of how we can kind of facilitate the type of interaction in more kind of ordinary type of activities. And there we're using kind of pre-built robots in kind of everyday situations. So that's kind of summarizing then the interaction and robotics part of RITMO. And again, as what we have shown you now is just kind of a few glimpses of all this, but you will hear more later. And Anne, I think over to you here now.
Yeah. Yeah, so as Alexander said, these are some highlights from phase 1. There is, of course, more fantastic research going on, and there are also very promising publications in the pipeline, but we primarily decided to focus on those that are already out. And also, yeah, a few words about plans for phase 2. If you want to hear more about our research, you can join the thematic panels in the afternoon. The program is posted on the webpage, and there we will have like smaller group of researchers talking about what they're doing. Okay, phase 1 has also been a kind of some challenging years, because we met some unexpected challenges, I would say. So during phase 1, the RITMO kitchens has sometimes, at times, been quite empty because of the pandemic. We had a fabulous start. So we kind of felt that we were building up something that was really, really fantastic, and then things were closed down. But there were things going on behind the scenes, especially a lot of Zoom activities. You can see here in the chat, also the Zoom activities had some challenges. Yeah, you are frozen on my end, maybe internet issue. Hopefully he will be back soon. I assume he might come back, and so on. But overall, I think it worked quite well, and I think we had a quite steep learning curve when it comes to kind of mastering these digital formats. Luckily, we also we were able to host a fully online conference. The whole center were engaged in the rhythm production and perception workshop, which took place in June 2021. It was also a challenge when it comes to digital formats. I look at Alexander because you were really, really key to making that event happen. But I would also say that was a highlight of 2021. Around 250 participants from all over the world, and a lot of interesting discussions going on. But then, happily, we have gradually come back to meet, at least in hybrid forms, with some physical presence and some online. We celebrated actually last fall with a get-together party. Turned out to be a bit early though, because the pandemic was not over. But I think we used like this little window of opportunities for being gathered physically. We also went on tour. So the yearly Tour de Ritmo retreat took place physically in September. We also squeezed in the Christmas party. I think that was the day, I think the same day actually, the whole country kind of closed down again. But it was great fun. Okay, we have today primarily talked about phase 1. We will discuss more about the phase 2 for tomorrow with the Scientific Advisory Board. We have also started discussing RITMO's phase 2 and exit strategy with the RITMO board. So we're working on that part of the next, hopefully 5 years. So the center, also the midway evaluation is coming up now for us. I think that's it. Or do you want to say a few words about the career development program?
We can take a few more things before we move on to the lab to look at the installations. One of the things that we have been working on also during the first part of RITMO is to develop a career development program for all the recruits at RITMO. This is something we have done with other centers of excellence at the university. And it's something that all RITMO recruits kind of go through, and it's also partly built into the regular tour, the RITMOs that we're doing. We have also been working a lot on data management and open research. This is kind of more kind of back-end work, so it's not kind of so flashy and visible on the outside, but it's extremely important when it comes to really systematically working with all the data that we have and trying to figure out how we can share it and archive it, etc., and also abide to the open research principles. So that's also something we are part of. We're also working on educational activities, and yesterday we celebrated that we had completed the first round of our new so-called MOOC, a massive open online course called Motion Capture, the art of studying complex human activity, where a lot of RITMO people have been involved in making this online course. And this course we are using for internal purposes, for training people to use the motion capture lab in this case in particular, but it's also open to the rest of the world. And I think, in fact, we have someone here today that actually took the course and wrote to us and said, could I come and visit? And we said, yes. So already now we kind of see that this is an interesting way of also connecting to people in the world. Should say that we are also starting to shoot and film a new pupillometry MOOC now that also other people have been involved in. So that will be hopefully ready in the fall. And we're planning also an EEG MOOC there. So I guess that's it for the first part of this event. And I think now we can move down to the lab to look at Dr. Squiggles.
Yeah, is Mike ready, or is it was planned for 11:30?
But yeah, let's just hope that he's ready down there.
Yeah.
So it will take a little bit of time to move down. So let's just move, and well, thanks for this first part here.
Yeah. And there's more coffee and more croissants, so feel free to eat and drink.
Huh?
well, this
Mike, where do you want us, man?
Just come in, stand anywhere. I guess disregard the sign that says no food and drink.
How much space do you need to save?
Yeah, come in, please. Yeah, no space. Yep. What's going on? Are people getting coffee out there?
People, like, some are a bit slow, so.
Okay, well, at least we're.
We can maybe wait a little bit more.
Yeah, well, we should wait at least until.
Syllabic. I mean, people are chanting syllabic. Yes. And I'm wondering if something that really just focuses on tax people better. And they're very noisy. From. Yeah, that's always a problem.
Because it's just from the weight.
Yeah. Oh yeah. Yeah, yeah.
You go by
Yeah, sure, I'll be around. Yeah, let's chat during lunch or something. What's your name, by the way? Thank you, nice to meet you. Thanks.
So there is sleep in there. Because it's a blurring of a lot of stuff.
Yeah, yeah. Well,
So
yes, I published an article about how to make magazines. They did not. They removed my knitting tutorial for the print. Yeah. So people are like, oh, we don't know why there aren't more women who are interested in these things.
yeah.
Are there more people still coming in?
Yeah. Well, I think I need to take into consideration the slope of the blurring of
So hi, everybody. Thank you for coming. For those of you who I don't know, my name is Mike, and I work here in RITMO in the Interaction and Robotics Research Cluster. And some of us in this cluster have been building robots that play music, some of which you see here. And so we're going to spend the next maybe 15 or so minutes demonstrating some of these robots to you. And then subsequently, some of these are set up in a way such that you can interact with them. So either after I've done demoing them or sometime during lunch, you're welcome to come back and play with these. So you can either kind of stick around afterwards and play with them, or you can wander off and get lunch and kind of wander back in later sometime within the next hour or hour and a half or something like that and play with these. And I'm not going to talk too much about the scientific goals behind all of this right now, but that's also something else you're welcome to ask me about during lunch. So there are 4 demos, and the first one is this thing over here. So these little octopus-looking robots, I call them Dr. Squiggles. And these are musical tapping robots. So they basically just sit there and tap out rhythms on whatever surface they happen to be sitting on. And they also listen through contact microphones, which is this thing right here. So the way I have this set up now, these 2 robots are listening to this robot, and this robot is listening here. And I'm going to play some rhythms here, and this robot can only hear me, and these robots can only hear this robot. And so once I start playing, what you'll hear is the robots. First, you'll hear them start to synchronize with my beat. So they'll kind of match my beat and tempo. And if I play the same rhythmic pattern over and over for a while, you'll hear them start to play something that is similar, although maybe not identical to what I'm playing. And then if I change tempo or if I change to a different rhythmic pattern, you might hear the music fall apart a little bit. But over time, you'll hear everything kind of come back into synchrony as the robots adapt to that change. Okay. So without further ado, I will do this. Thank you. Okay, so demo number 2. So these robots don't really deal with pitch at all, even though some of them are sitting on pitched instruments. They don't really have any concept of what pitches they're playing. But because I wanted to study that a bit more, I built these things over here. And so these are acoustical pipe organs. So this is an organ pipe. And so each robot here has 8 organ pipes, and consequently, this robot can play 8 notes. And then each robot is listening, this time just through a regular like omnidirectional microphone. So I'm going to sit here and play guitar, and each robot can hear me, each robot can hear itself, and each robot can hear all of the other robots. So the robots all hear everything, basically. And because each robot can only play 8 notes, no robot by itself can play very much interesting music on its own. But somehow if the robots listen to each other and work together, then maybe they can create interesting music kind of in collaboration with one another. So basically what happens is that every moment in time, this robot needs to listen and figure out whether or not it's appropriate for it to play any of its 8 notes. And we're using some kind of fancy machine learning thing for that. And so we have air.
Can I just ask, do they all have the same 8 notes? No.
No, they're mutually distinct. So it's 2 octaves total. Yeah. They don't really distinguish between musical and non-musical sounds, so they just play along with whatever. Yeah, so that's that. And then, so I'll move over here now. So this is a different project, not entirely related to the other 2 things that I've shown you. This is something that I'm calling Professor Plucky. And it is a, kind of part of a prototype guitar robot, well, obviously. And it doesn't really fret the strings at this point. It only plucks the strings. And the reason I built this is because we were interested in studying robot movement and how the movement of a robot affects the way that people interact with it. And so, this one is not a kind of interactive demo, but I'm just going to press play on my laptop. And what you'll see, first of all, this will play a little bit of music without visually appealing movement. So you won't really see it moving very much. And then subsequently, it will play the same music kind of with visually appealing movement. So. And it looks like maybe one of these is malfunctioning a little bit, which is why more recently I've been working on kind of a more sophisticated robotic plucking mechanism. So stay tuned for this kind of thing. And then, so the last demo is robot built by Mushtaba, who's going to demo it for you.
Hello everybody. My name is Mushtaba, and I'm a PhD at RITMO working with robots. So here we have a prototype of a drum robot. So this might be not as interesting as what Mike was showing. But the aim of the robot is to learn drumming tasks by interaction. So the first thing is that we need a body of a robot that can play drums with specific physical properties. Here, this robot has 2 degrees of freedom actuated by just one actuator. The actuator is a special type of direct drive servo motor. And the thing about this motor is that it is able to control the force and speed and position of the joint in different control modes. And the second degree of freedom of the robot is a passive joint which has springs. The springs are used here to make the robot be able to use the rebounding forces of drum membrane. So here I can show some basic drumming patterns just programmed to play by the robot. But in future, the robot is supposed to learn these patterns by playing and interacting with the instrument, and maybe in future with other instruments and other maybe drummers or players. So the drumming tasks may be as simple as a very single stroke drum roll like this. As you might understand, the frequency of the drum roll is really important, and it has a really has a physical connection to the stiffness of the springs here. And this stiffness of the spring make the robot able to play other drum rolls like a double stroke drum roll like this. And all these different patterns can be performed by the robot if the robot can learn how to control or how to update its controller to generate these kind of patterns. And eventually it might learn more complex rhythmic patterns like this one. As you might recognize that this is kind of combination of double and single strokes, and this might emerge by changing the control patterns of the control of the robot. Yeah, this was it, and we have other things to show.
No, that's it. So that concludes the demo. It's very synchronized.